Good morning, everybody. Good morning. Unfortunately, I can't say good morning to the people who would otherwise be watching online because the system has broken down temporarily. It will be recorded and be available some time in the near future. Now, not many messages at all. The boards are being sent around where we're asking for your ideas for subjects for next year. Also interest groups that you may think could be started. So also people who would be happy to do the votes of thanks, etc. So if you just have a good think about that and add that to the boards. Right. Last year we had a very good series on Antarctica. We covered the birds and the animals. We covered the human efforts in Antarctica, the management of the base, and at the end of the series, it was clear we had a huge gap, and that gap was with regard to the science taking place in Antarctica. Today, we are very fortunate. We have Professor Tim Naish to talk to us. Tim's come here specifically to the South Island from the north to speak to us, and he's fitting in a number of skiing expeditions as well. So I'm pleased to introduce Professor Tim Naish. Professor Naish was director of the Antarctic Research Centre at Victoria University of Wellington until 2017, when he took up a Royal Society of New Zealand James Cook Fellowship. He's Professor of Earth Sciences and is currently seconded part-time to Antarctic Research New Zealand, where he leads the Ice Ocean Atmosphere program, focusing on climate change with emphasis on polar ice sheets and sea level change. He's a committed communicator on Antarctic and climate science issues. He serves on a number of international science organising and governmental advisory committees, including World Climate Research Programme and the Scientific Committee on Antarctic Research. He co-leads the New Zealand Sea Rise Programme. His team was the 2020 Prime Minister's Science Prize winner. He has received the New Zealand Antarctic Medal, and I think I've got these next words correct, the Tinker Muse, is that correct? The Tinker Muse Prize for Antarctic Science and Policy. He's a Fellow of the Royal Society of New Zealand. Professor Naish, and Karen is accompanying him, his ski partner. Professor Naish, we look forward to your address very much.
Oh, that's good. Yep. Now you can all hear me? Yes. Oh, great. Thank you, Tony. That was very generous introduction, and it really does look like U3A is alive and well in Christchurch. It's a really great turnout. So happy to be here, and yes, as Tony said, made this trip specially for you lot. But also fitting in a bit of skiing. But I think the weather's not going to play ball, so we'll just have to see how it goes. Okay, Now, Tony gave me a fairly large brief. He said, talk about science in Antarctica. And I didn't really, I could talk about a lot of things, but what I've decided to do is to stick to an area I'm quite passionate about, and that is, how is climate change affecting Antarctica, and what does that mean for us in terms of the impacts that the world is facing as a result of climate change. I'm a geologist. I love rocks, I love drilling. I've been involved in a number of drilling projects in Antarctica with many other countries where we've drilled the geological history and we've understood how the continent and the ice sheets and the climate behaved in the past. And so that's where I come from, but these days I'm very much interested in what that means about the future we're heading into. So it's a window from the past. These windows from the past are really very important when it comes to future, because a lot of the changes that we're going to see, we haven't seen for millions of years. So how do we know our models are right? How do we know the climate we're predicting will actually play out? And one of the ways we do that is to use these models on past warmer climates to get an example of what happened when the world had higher levels of carbon dioxide in the atmosphere. So let's go back to, oh yes, I have to switch that on, don't I? There we go. Okay, so let's go back quite a long time and just remind ourselves that Antarctica was not always like it is today, and in fact had lush forests, had dolphins, fjords, and was a pretty warm place. And so geologists, the vegetation, the remains of vegetation can be found all over Antarctica. There you see 300 million years ago tree rings on a tree and stumps that are preserved, petrified forests, and glossopteris leaves. So there was a really thriving, lush, near-tropical vegetation back then, and it might have looked something like this 100 million years ago. So this is the Cretaceous period, where Antarctica was part of a supercontinent called Gondwanaland. And about 100 million years ago, it started to break up. And so Africa, South America, Australia, all the continents sort of left Antarctica alone on the South Pole. And so as a continent, it's been there on the South Pole for the last, 100 million years, pretty much. And we know that it was the polar regions were warm. And so that's a bit of a challenge when you're thinking about how do you melt all the ice on this planet. It's a challenge for our modelers. What level of carbon dioxide do you need in the atmosphere to warm the planet to that sort of level? And we certainly do not want to go back to that level of carbon dioxide. And so those are the trees you might have seen had you been living there in the Cretaceous: cycads, ferns, monkey puzzle, and probably one of the warmest times in the recent past, which is still 50 million years ago, was the Eocene. There were mammals, no dinosaurs on Antarctica, but there were mammals. And this is sort of down the bottom here what it looked like. So you can see that Australia is still quite close and the Drake Passage hasn't really pushed through here, but Antarctica was beginning to separate and become isolated in its own right. And up north, this is what the northern continents looked like, and there was this big Arctic Ocean. It was probably more like a bit of a swamp, actually, and it was full of this thing called Azolla. So that was a very shallow sea up here, and down here, the continents were starting to push apart. Carbon dioxide was probably more than 1,000 parts per million in the atmosphere. The temperature was probably 10 to 12 degrees warmer than it is today. So this is extreme global warming. This is a world in which we're not going to go into, hopefully, but it's at the very high end of the global warming scenarios for the future. And the pollen records there, when you drill into the sediments and you pull out the pollen, you can reconstruct the vegetation. And you've got these baobab trees, and you've got palms. In the north, you've got crocodiles, and you've got dolphin remains as well around Antarctica. And this led to a very important Nature paper a few years ago that demonstrated that there was near tropical warmth in Antarctica 50 million years ago. Okay, so what has happened since then? And that's a couple of complicated graphs really, but what I'm trying to show here is temperature has declined. So this is temperature, it was 12 degrees warmer back here. This is present day. This is 50 million, 60 million, 65 million years ago. And this is carbon dioxide. So essentially what's happened is carbon dioxide in the atmosphere of Earth's atmosphere has declined from up here at about 1,000 parts per million down to present day levels or pre-industrial levels of 300 parts per million. And then of course today we're back up at 400 parts per million. And so as the greenhouse gases have declined, the atmosphere has cooled, the planet has cooled, the oceans have cooled. And that's the story. There's a lot of detail in that, which I won't go into, but about 15 million years ago, we see the last evidence of trees on Antarctica. After that, no trees, no higher plants. There's a few other things, but we lose our trees. And they weren't substantial trees, they were small, stunted beech trees and things like that. There is a bit of a debate in the literature with scientists of whether there might have been refugia that existed near the coast that then got big again in the Pliocene. That's an open question. So that was 3 million years ago. But certainly since 3 million years, Antarctica has been a cold place isolated by the deep Southern Ocean and essentially what it's like today. So you have to go back. I guess my message here is you have to go back 3 million years to find a window in the past when our climate is similar to what it is like today. So today we have 400 parts per million carbon dioxide in the atmosphere. And we've seen a degree of global warming, but we'll see more. The climate system hasn't come to equilibrium for that amount of carbon dioxide in the atmosphere. So I think my next slide might get us into this. Oh no, we're on our way. So this is evidence. Remember I said 15 million years ago, the last trees, there's the last evidence for trees on Antarctica, and this is a very complicated map, but this is essentially Ross Island down in here in the Transantarctic Mountains, and we were up there with a team in 2016 and drilling sediments, and these are old lake beds, so there were lakes there with small nothofagus shrubs, so there was a tundra vegetation up there 15 million years ago, and you can see the nothofagus leaves. You can actually just dig into that surface, which has sort of been untouched for 15 million years, and you can just, with your shovel, pull up these old beech trees, evidence of these leaves and bits of wood that are so fresh you could almost burn them. So that's when we think things started to cool significantly around Antarctica, and the East Antarctic ice sheet got very big, and the West Antarctic ice sheet got big as well, and that essentially terminated this period of warmth. And we think carbon dioxide was probably 500 parts per million. So that's a future that we may end, that could be where we're heading. Whether we'll see trees grow again on Antarctica depends on a lot of other factors, but those temperatures could come back. Okay, so that's today. The highest, driest, coldest, windiest, remotest place on Earth, but absolutely fantastic place, spectacular. But it's got a lot of, it breaks a lot of records in terms of its climate, in terms of how much fresh water. 70% of the world's fresh water locked up in ice, 90% of the world's ice, and if it all melted, which it has done in the geological past, sea levels are 60 metres higher around the world. Now, it won't do that straight away, but it's starting, and we all know it's starting because we hear about it in the news, and we've heard about this thing called sea level rise. So yeah, that's the potential. If you keep cranking the temperature up, you will remove all that ice. So let's talk about what's sort of happening right now with it. Okay, see if I can set this off. This is a little movie. There we go. And what you're looking at there is the Antarctic Peninsula and South America, and you've just gone through the Drake Passage. And we're peeling back the surface ocean. That's the Antarctic Circumpolar Current in green. And now we're heading into the Ross Sea region. Scott Base is right in there. And this is what's happening at depth. This is one of the factories that produces dense cold water that spills off down canyons into the deep ocean and makes its way up the side of New Zealand, into the Pacific Ocean, and ultimately right up to the Arctic, and drives the ocean circulation currents around the world. But the factories that produce that dense cold water are in the Ross Sea and in the Weddell Sea. And so we think of it as an engine room, and it's certainly important in terms of pushing ocean currents around the world, which then pushes heat around the world. Right, what do we got next? So that's the pattern of ocean circulation. You can see these blue lines, these are the deep cold waters produced around Antarctica. They spin off up into the Pacific Ocean where they upwell, and they ultimately head up the Atlantic, the Gulf Stream, nice and warm, which brings nice warm climate to places that should be colder. And then it sinks again up around the Arctic, around Greenland, and comes back as a cold current to Antarctica. And that's just turning the ocean circulation, and it's controlling the heat of the planet. And this movie was on ages ago. I quite liked it because it made paleoclimatologists like myself famous. And, we'd found evidence that, if you switch the Gulf Stream off, then you can plunge the Northern Hemisphere, particularly Europe, into a mini ice age. And that happened, actually, about 13,000 years ago. And so the question today is, if you melt Greenland, can you put enough fresh water into the ocean to then switch the Gulf Stream off? Because fresh water tends to cool the circulation because you need the density contrast. The models would say no, that's not going to happen. So a little reversal, a little mini ice age, like in the movie, is not going to happen. It's not going to save Europe from the sort of temperatures it's been seeing over the last few weeks. Yeah. So this is a bit old now, this slide. It's not 2019 is the record year. Well, of course, we know that the most recent years have all been records, and this year's turning out to be another one. But you can see the pattern there, right? That's global average temperature since the Industrial Revolution, since we started using coal, oil and gas. And, you might, not every year's a hot year, but the trend is very clearly, and each successive decade since 1960 has been warmer than the one prior. So this is unequivocal. We don't debate this anymore. The world is warming. And the world is warming because of us. And we don't debate that anymore. So this is carbon dioxide over the last 10,000 years, nice and level. And that's great. Our climate's been very stable for 10,000 years, and our species has evolved. Our civilizations have evolved because of that. This is the level of carbon dioxide in the atmosphere in the last 230 years. Look at the last 30 years. And that's unprecedented since the Pliocene, since 3 million years ago. So we're now into uncharted territory, really, as human beings. Our species is only just 3 million years old. So you have to go back 3 million years to get to a time that when we last had 400 parts per million carbon dioxide, and that can tell us some interesting things about what the world will be like if we do nothing about it. And the other interesting little fact, I was on the IPCC and in the previous report, the Intergovernmental Panel of Climate Change, and we made a very strong statement. We said it's virtually certain that we cannot naturally go into another ice age because of the carbon dioxide that's in the atmosphere. So as a species, we've knocked our planet off its normal climate trajectory. So we've managed to do that, which is quite an amazing thing. So CO2 needs to be below 350 parts per million for us to go back into an ice age where, we could talk about that later, how that happens. So, 3 million years ago, this is what Antarctica looked like. We know this from some of these drilling projects I was telling you about, the Andril project, some of the ocean drilling that New Zealand scientists have led and been heavily involved in. And what we discovered is the Ross Sea was 5 degrees Celsius. Right now it's almost -2. There was no sea ice, there was no Ross ice shelf, there was no West Antarctic ice sheet. So the bottom line is, if we keep this level of CO2 in the atmosphere and we wait 1,000 years or so, then we'll lose all of the West Antarctic ice sheet, bits of the East Antarctic ice sheet, and sea level will be around about 20 metres higher. So that's the road we're on, that's the road we've kicked off, and the question really becomes, can we stop that train? Can we prevent meltdown of the West Antarctic ice sheet? Some scientists say, no, it's too late. Some modelers have said, we think West Antarctica is already under irreversible collapse. Others, and people I work quite closely with, are still hopeful. The models suggest that the tipping point is nearer 2 degrees of global warming. So we all know that that's the Paris target, that we're trying to keep global warming under 2 degrees above pre-industrial. We've done a degree, we've got another degree to go. But it could be 1.5, and that's why this government and governments around the world are pushing for 1.5 as the stable climate for the future. And this is one of the major reasons. If we warm more than 1.5 to 2 degrees, we may commit ourselves to 20 metres of sea level rise over 1,000 years or so. It's not all going to happen this century, but some of it, and certainly next century, metres will happen. And so we're really close to that tipping point. We don't know exactly where it is, and it's not looking like we're going to stabilise global warming at 2 degrees if you look at how countries are going at the moment. So that's an intergenerational thing. We won't have to deal with it. Our children will start dealing with it, but generations down the track will be dealing with it. Right, another little factoid. Where's all the heat gone? All that warming so far has gone into the ocean. 93% has gone into the ocean. Our planet would be 36 degrees warmer if we didn't have an ocean taking up the heat. So the ocean's our friend. It's taking up a lot of heat. It's also taking up a lot of CO2, which acidifies the ocean, so it's bleaching coral reefs and that sort of thing. And ultimately, that heat in the ocean is not our friend, because once you put it in there, it's in there for hundreds of years, and the Antarctic ice sheet sits largely in the ocean, and it's warm. And most of the heat's gone into the Southern Ocean around Antarctica. So, this is part of the problem. Even if we stop the CO2 now, is there enough heat in the ocean to do Antarctica in any way? Certainly the bits that sit below sea level. Yeah, it's not very uplifting stuff, is it? Okay, let's talk about sea level. So sea level has risen, that's a fact. It's risen 20 centimetres since the Industrial Revolution, since we've been heating the planet. We know that from tide gauges. We know that now more recently from satellites. So sea level rise is a thing, and it's because of the global warming, and actually it's largely because of all that heat that's gone into the ocean. When you heat water, it expands, and that's what's happening with that heat in the ocean. Of course, the glaciers and the ice sheets are contributing about the same amount as the ocean heating, but in the coming decades and centuries, it'll be the ice sheets that are the main drivers of sea level rise. You can only heat the ocean so much, but then after that, it's the 60 metres locked up in the ice sheets, and plus the Greenland ice sheet that start to contribute to sea level rise. Sea level rise is not even around the world, and these hot areas here, these red areas in the South Pacific and Asia, where billions of people live, are getting 3 to 4 to 5 times more sea level rise, because that's where the ocean's heating the most, around there. And so it's, there's a bit of an inequity, and I've just been at a conference in Singapore, which I offset, and it was really confronting to see the impact of sea level rise, not only on rich countries, but on poor countries. So countries like Singapore are going to build a wall around the whole island. They're going to spend $100 billion. They've already put $10 billion into it. And they're just going to fence themselves in like the Netherlands, but a lot of countries just don't have any ability to adapt because they're so vulnerable and so close to sea level rise. Obviously, we hear about the Pacific Islands. And yeah, that's the inequity. The people who didn't really put the carbon dioxide in the atmosphere are at the front line of climate change, whereas the developing nations who got to use this cheap energy to get developed are the most able to protect themselves, basically. So what's causing the sea level rise? I think we talked about this, but the ocean's heating, the ice sheets are melting. The glaciers are really interesting. Like glaciers like New Zealand's Southern Alps, like the Himalayas, they can give another 0.5 metre of sea level rise before they're all gone, and they're all likely to be gone in the next century if we continue on the track we're on. So they can't give too much more to sea level rise, but they are very important for water supply, particularly in Asia, and there's about 1 billion people in the Himalayan area, Hindu Kush area, that rely on those glaciers, which will be gone. And then the ice sheets, of course, become a problem ongoing for many centuries into the future. I don't know how much I really want to get into this, but just to point out that Antarctica is the elephant in the room when it comes to sea level rise, in that we just don't know how it's going to respond. But we do know that it's capable of doing things very quickly, and once they start, they're irreversible and you can't stop them. And that's largely because of that heat that is in the ocean. So this is a cartoon of the edge of the ice sheet, and the ocean, the warm water's getting up, and it's nibbling away under the ice shelves, which are the floating extensions of the ice sheet, and it's getting into the underbelly of the West Antarctic ice sheet. And you can see this is where the warming has occurred the most, and along West Antarctica. And these big red circles are really where the ice is melting the most, where the ice shelves are melting. And the question is this unstoppable? Have we got enough heat in the system, or can we still save it? So once the ice shelves go, and here's a lovely, well, it's not a lovely example, it's an example from 2002, the Antarctic Peninsula. It's about the size of England. And within a month, that ice shelf shattered and collapsed because of ocean warming and atmospheric warming. And then the glaciers on Antarctica flowed into the ocean 10 times faster because the ice shelf had gone. You can sort of think of it as like the flying buttress on a Gothic cathedral. When you take away the buttress, the church falls down. If you take away the ice shelves, the ice sheet falls down, and under gravity it flows into the ocean. And once we lose those ice shelves, that's the tipping point. Then we can't bring it back. So that's why the science community is a bit, we're not entirely sure because we've got a lot of ice shelves still there. We think we may still be below that tipping point. So yeah, but we're close. So depending on what we do with our emissions in the future, we will have sea level rise. We can't avoid that. We will have 0.5 metre of sea level rise globally if we achieve the Paris target, and we will have almost 1 metre or more if we do nothing. So we can't avoid sea level rise, and so in a way, if you're a planner, if you're in the city council, and you're thinking about Christchurch and South Brighton and the vulnerable parts of Christchurch, you can plan for 50 centimetres. That's in, that's locked in, that's baked in. But the question is, what do you do about if Antarctica does melt rapidly and you end up with 1 metre of sea level rise? And the latest IPCC report, which just came out last year, it said, okay, you should be planning for 1 metre worst case scenario. However, if Antarctica does something that we think it's capable of but just don't know enough about, you can't rule out 2 metres of sea level rise. And then into the future, into the next few hundred years, you're looking at tens of metres of sea level rise. So the blue scenario is Paris. So these are things that are underway and can't be stopped. And all we can do is minimise how much we get, whether we end up with 15 metres of sea level rise by 2300, that's only 300 years away, or whether we can keep it under a metre or at least a couple of metres. Yeah. Yeah. So, sorry, it's a bit doom and gloom. I'm going to show you a positive future right now with these movies, and do feel free to ask a question if I'm not explaining something quite right, or you're not understanding it, or we can save those to the end as Tony suggested. Okay, so I'll set this off. Two futures. The one on the left is we reach the Paris target. The one on the right is burn, baby, burn, keep burning fossil fuels. And you watch West Antarctica. The one on the left's a good future. The one on the right's not a good future. So you've got the, I don't know if you can see from the back, but you've got the years rolling by up the top, and we're getting towards the end of this century, 2100. Look what's happened to on the right there. That's 100 years away, but look what's happened on the left. It's stable. So that's why we still think there's a chance. We don't think enough of the ice shelves have collapsed. They're still holding it together, and so that's the positive future. It's not a very likely future, but if we could achieve 2 degrees of global warming and the Paris target, we get the future on the left rather than the future on the right. And this is playing out now to, what are we at there, 2500, I can't quite read it. So that's a few hundred years into the future. Okay, so yeah, that's the big question. How close are we to this tipping point? 10 years, we'll be at 1.5 degrees on the current trajectory. And 25 years before we're at 2 degrees. So there's big global impacts, and I don't want to be too depressing, but at this conference in Singapore, there was a guy from Bangladesh who's responsible for their policy on how to adapt. And they're facing, by 2050, they're facing 18 million people displaced because of, and that's unavoidable. So that we can't stop that apart from helping them build walls and adapt. And they've got very low adaptive capacity, so, you know, there's going to be a refugee situation there. Yeah, I don't want to go into too much of the depressing stuff. But 700 million will be affected by high tide flooding around the world by the end of the century. That's what happens in Shanghai by the end of, by 2050. Oh my goodness. It's probably the warmer scenario though, rather than the Paris scenario. And that's London. Let's talk about New Zealand, because I don't know if you've been watching the news lately, but there's been a bit of stuff on sea level rise, and our group released some new projections for New Zealand. So you can go onto the website and you can click on your place, a dot near you, every 2 kilometres around the coast, and you can see what the sea level looks like for you. And this has been important timing with the National Adaptation Plan the government's just released, and basically saying we don't know enough about what we're in for, what we're adapting to. And so that's the sort of game we're into now, is trying to improve the knowledge of the risk of, and particularly with sea level rise is where I'm interested. So we all know New Zealand goes up and down, right? Earthquakes, but between earthquakes the land is rising and the land is sinking. In some parts of the world they've used so much groundwater, like in California, the land has gone down 1.5 metres. In Tokyo it's gone down 4 metres because of all the groundwater they've pumped out, and so they're now building walls. In New Zealand, where it's not groundwater that's causing the land to go down, it's tectonics. We're on a very active plate boundary. So we've got the Pacific plate going under the Australia plate. We've got the Southern Alps going up. We've got other parts of New Zealand, the lower North Island and the upper South Island going down at the moment. But then it bounces back up when we have earthquakes. You've got to factor those land movements in to your local projections. We've been doing work with Environment Canterbury on this, because you guys live in a very tricky area because of the earthquake. It's very hard to predict. Land is doing crazy things around Christchurch after the earthquake. In Wellington, it's easier to predict. Our land is going down at about 4 millimetres per year, and it has been doing that every now and then. An earthquake like the Kaikoura earthquake affects that, but we haven't had a major earthquake since 1855 in Wellington, and so we can expect that rate to continue, 4 millimetres per year. Sea level's rising at 4 millimetres per year, so that doubles the sea level rise. It means you get 8 millimetres per year. And that means what you thought was coming, you had time to prepare for, you have half the time to prepare for. So that's why it's been in the news a lot, and we're not intentionally wanting to stir up trouble. And in fact, the house prices haven't responded. It's really interesting. The house prices haven't responded. People don't. Yeah, it's a really interesting thing about the human psyche. People don't really want to believe it. And people don't leave. There's an island in the Philippines which gets wiped out every second year. They've been offered land on shore to be relocated, but they don't. And so at high tide, the kids don't wear shoes to school because the floor of the classroom gets water. So they're sitting there at their desks with water around their feet. And they don't want to move because they've always lived there. There's cultural, there's social, and there's economic. They fish, and the economy's gone if they move. And if you're rich, like New York City, you build a wall because you don't want to move. So we've got an active conversation around managed retreat going on in New Zealand right now. South coast of Wellington's a really interesting area. I've been talking at town hall meetings there. People don't want to move, they want to be protected. Yet we have to figure out a fair and equitable way to move some communities that are the most at risk and then not allow development to happen in stupid places from scratch. You know, a lot of that goes on in New Zealand even now. Okay, I'll get back on track. Okay, so for us, we have a coastal hazards guidance from the Ministry for the Environment, and that gives one set of numbers for New Zealand planners and decision makers, depending on the emissions scenario, Paris or worst case scenario. However, one set of numbers does not fit for New Zealand, and so we're really lucky. We've got a lot of good network of GPS data and satellite information about how our land is deforming. And when we use that, we get a much better picture of what the land's doing. And this is a bit complicated, but pretty simply, the white areas are pretty stable. The blue areas are going down. So, you know, there's a bit of blue around Christchurch. But look at this. This is the hot spot. Lower North Island, Upper South Island is going down at greater than 2 millimetres per year. Auckland is going down. We never knew that. We thought Auckland was stable. But apparently Auckland's going down. So what does that mean? You go onto our website and you click on a dot, you can zoom right in and you can click on your house in Petone on the waterfront, and then you can bring up a graph and you can see the old sea level rise, which is this lower line, which is what New Zealand planners were working on for Wellington. But when you add the vertical land movement, this is the sea level rise. It doubles. So this is years along the bottom. This is amount of sea level rise. So basically, you get to 30 centimetres, if that's your number, or 20 centimetres, twice as fast as you would have if you were using the old information. So vertical land movements matter. And we've just seen this in Wellington, another one of these extreme events. This is the Days Bay Road round to Eastbourne. And, you know, this isn't even the 100-year flood. But for most places around New Zealand, 30 or 40 centimetres of sea level rise means the 100-year storm happens every year. So for Christchurch, it's 40 centimetres, and I'll show you South Brighton in a minute. And for Wellington, it's 30 centimetres. So what that means is, there we go, it's a bit faint. We thought we had till 2070 on the old curve, but we might only have till 2030 before the 100-year storm becomes an annual event. And that'll essentially cut off this. This road's already a problem, So, I guess it'll be ferry access or boat access. Or perhaps they'll build a new road. But these are the things that are really very close to becoming issues. Here's you guys, and you won't be able to read that. It's a Tonkin and Taylor report for Christchurch. And the blue areas are the bits that go under, and I can't remember what level of sea level rise, but they're the most vulnerable bits. But, before the earthquake, Christchurch was fairly stable. It was sinking a little bit. Since the earthquake, South Brighton, is this South Brighton? It is, isn't it? That's going down at 8 millimetres per year since the earthquake. And I don't know what that is, whether it's the ground readjusting, how long it will continue, we don't know. Environment Canterbury are very worried about it, but its pre-earthquake rate was only 0.8 millimetres per year. So how long have you got, and I hope there's not too many of you from this area, but how long have you got before South Brighton becomes an issue? So let's look at our maps, our graphs. This is the information you would have been using if before we put in the vertical land movement at South Brighton. And so you would have had 2070, 2080 before that 100-year storm was an annual event. But now you've really only got till 2030. So it's, but we don't know if that subsidence will continue and how long it will, because it's not like the subsidence under Wellington. When you have an earthquake, things go crazy for a decade or so, and then maybe they come back again to normality or what was. And so, these are things that are a real challenge. So yeah, as I was saying, the rich get walls, that's Japan. And this is this poor island in the Philippines that when it gets a hurricane pretty much gets wiped out and has to be rebuilt. But they're pretty easy to build huts because they're just shacks really. So they just put them back up again. Maybe put them on stilts. And then, what do? Like the Thames Barrier is no longer capable of keeping London safe. I guess this is sort of the final slide, Tony, and I realise that when I give this talk, it's a little bit depressing. But I think I'd want to finish up by saying information is power, and with sea level rise, it happens slowly and it may go on for a long, long time, but we have time. So I think this information gives our infrastructure providers, our councils, our planners, and our public a chance to figure out how long you've got. And when we put this information out, we probably had 200 emails from residents who wanted to know when they should sell their house. and we just really concerned. We're sort of like, oh gosh, we're giving you the information's out there for the councils, so you've got to talk to your council. But there's time, right? I mean, South Brighton's an extreme example. You've got 10 years before you might be in quite a bit of trouble there. Which isn't very long, is it? The south coast of Wellington's another one. They're very concerned. And so, local government, central government, with this sort of information in their hands, there should be no excuse for not doing something about it, but it needs us, it needs people to also not put their head in the sand, but to push our governments along to do the right thing. And on that note, Tony, I don't think that's very uplifting either, but I'll hand back over to you. Sure.
Right, question time.
Down the back, there's a hand.
There's a hand down the back. Where's the hand down the back?
I've often wondered how effective these walls are that people keep thinking is the answer to everybody's problem. You can't fight nature to that degree, surely.
No, I agree with you. I mean, if you're follow the Dutch example, you can, but that's, even they are looking at their walls and making them higher and getting bigger pumps to pump the water out as they go lower and lower. Singapore will build a wall, but if you build a wall, you have to build it all the way around. You can't just build it in front of your house. Otherwise it will just go around your neighbour's place. And we've seen examples of that on the west coast of the South Island. Anyway, I agree with you. It's not the ultimate solution.
Ivor Watson. I understand that there's part of the Antarctic where the actual snow is accumulating rather than decreasing. Maybe you'd like to comment on that and what the effect is and why is that happening?
Yeah. Well, that's global warming as well. And we saw an example of it just recently with that atmospheric river. There was a heat wave that hit Antarctica, and around the coast it melted, but they had a snow bomb go off up high on the East Antarctic ice sheet because that's just a huge amount of moisture, and when it gets cold, it turns into snow. It's a bit like we're getting much more heavy rain events because there's more moisture in the atmosphere because of global warming. When you heat the world, you evaporate more moisture out of the ocean and put it in the atmosphere, and in the Antarctic it turns to snow. But the models show that the melting that's happening around the edges will outpace the snow that's falling. So it won't save Antarctica, but it could slow things down. And actually I was at a meeting not so long ago where the Chinese and the Russian representative came up to me and said, our scientists think Antarctica's growing because of the snow that's accumulating where they measure it at their stations. And they were climate change deniers at this meeting. They didn't, and so that was their evidence that Antarctica wasn't melting. But it's a great question, you're absolutely right. Parts of it are getting more snow, and other parts are losing snow.
Graham Robertson. There was a bit of discussion at one stage about seeding clouds, putting various substances up in the atmosphere, and one can think of a lot of reasons why that might not be a smart idea. Where's that getting to now?
Yeah, that's a really good question too. So there's two things. There's solar radiation management, which is what you're talking about, seeding clouds, making the atmosphere more reflective. And the other one is direct carbon removal. I think direct carbon removal is the way we want to go. If we can develop it at scale and we're able to pull the carbon out of the atmosphere, a lot of people put hope in that. Maybe not right now, but towards the end of the century. Can be used. There's no technology that can do that at the moment. The solar radiation management is dangerous because it could do things you don't want it to do. It might, it's sort of like putting iron in the ocean to seed. So you put iron in the ocean and it's a nutrient, and then the phytoplankton bloom. They suck down CO2, but then a whole bunch of other things happen to the food chain and the ecosystem that you didn't want to happen. So I think the short answer, and my colleagues would all say this, James Renwick would say this, don't put it in the atmosphere in the first place, is the easiest way to control climate change. Technology may save us, but there's nothing obvious on the horizon. Yeah. Right at the front.
Andy Shand. Before climate change became an issue, I remember listening to a geologist, I think Dr. Kirk from Otago, and he was talking about how the South Island tips and the western part goes down and the eastern part comes up. My memory is he said in 1066, the sand hills at London Street near Woodham Road, that was where the tide was. And if you go back to the time of Christ, the tide was at Nancy's Corner, which is at the bottom of Riccarton Road. So there has been, according to his story, there's been quite a lot of rising here. Yeah. And if you carried on from where his suggestion was, we might be rising faster than the climate change.
Interesting. And you're right, actually. So is that Bob Cook? Was it Bob Kirk? I was quite a young, I was a student, I remember him. Absolutely, the land is rising and falling for natural reasons, for normal natural reasons. And if you live on the Bay of Plenty, I didn't show you on the map, but there were some red dots there. If you live near a place called Matata, Pikawai, Matata got a lot of flooding, but Pikawai, the land is going up at a much greater rate. So you're going to keep your head above sea level if you live there. So there are some places which will be where tectonics or natural land movements will keep them ahead of sea level rise. That's not common. But you're right about it's really important to know the historic pattern of sea level. Like you say, just a few thousand years ago, sea level might have been a metre lower or a metre higher. And so we work a lot with people who reconstruct the natural pattern of sea level so that we make sure that we're taking that into account. We're not just ignoring it. So you're right. But in Wellington we get people say, oh yeah, but if we get a good earthquake, we're saved. It's like, all right, the earthquake will save us theory. Yeah. You guys you know what that's like.
The biggest problem I have is to decide whether this is a natural phenomena or introduced by man. And in 1958, there was a professor down at Scott Base studying the ozone layer. Yeah. And he reckoned that there was a big hole appearing, which was allowing the Earth to warm up. Mm. But with all the civilization going on, to me it seems out of control.
Yeah. My dad is a scientist, and he and I have lots of colleagues, actually, not lots these days, but did have lots, and particularly geologists, they're unconvinced, because they know the natural pattern of things. And but I think, like I said right at the beginning of the talk, the world is warming, and the world is warming because of us, and the science on that is now in, and it's incontrovertible. I think with models, there's a bit of a uncertainty. People go, well, is that model really right? Yeah, I agree it's going to warm, but is it really going to warm that much? Is sea level really going to go up that much? And all I can say to that is that we've been modelling for 30 years now with computers, and every time we take the measurements, the models predict this, and then we measure what's happened, and the models are on the low side. Things are warming faster, and things are getting, I don't want to say out of control, but yeah, it's the models of anything are underestimating the future rather than overestimating it. You had a lot in that question and that I was thinking about, but yeah, I think New Zealanders, we don't really believe it till we see it, and I think we're starting to see it more and more around the world with these crazy wildfires, the heat waves in Europe, and one swallow doesn't make a summer, but these are many, many swallows now that are painting a pretty good picture that is a scientifically certain trend. So I don't know where we're going to end up. I'm an optimist. I'm hoping we'll land nearer 2 degrees and we'll be able to deal with many of the impacts, particularly in a place like New Zealand.
Tim, answer me just one simple question, will you? And that is, are we rebuilding Scott Base in the right place?
Margaret, I knew you'd ask the hard question. You don't want to get me started on Scott Base, by the way. But the answer to that question is they commissioned us to do a study on tsunami, sea level rise, and because they're building it from scratch, they're knocking down the old Scott Base and they're going to build a completely new one. They can pretty much put it where they want, and so they are putting it high enough to avoid sea level rise, tsunami. Don't know about Erebus. That can't. If that goes off, it goes off. Yes, I thought you were going to ask me a different question about Scott Base, but yeah, it's resilient, and it should be for that much money. Let me just say that. Yeah.
Can I thank you for a fascinating talk? I don't think I'm less frightened than I was before, but I'm not probably more frightened either.
Right.
There's not a lot really to say, except I have a much better perspective of where we're at,
Yep.
and probably as you have a little bit more perspective about where we might be in 10 or 20 years.
It's up to us.
Yeah,
We've still got the futures in our hands.
Yes.
Yep.
Yes.
Especially the young ones.
Right.
That's what I tell my kids.
Right.
We caused it all. You have to solve it.
Well, that's exactly right. And those of us who've got hair as white as mine can, say that even more effectively and loudly. Grandchildren and great-grandchildren, maybe.
Yeah.
I know that you have suggested that you would like to give your donation to the Save the Children Fund.
Just put the thing up to
Sorry. Tim has kindly offered to give his donation to the Save the Children Fund, who I'm sure will be most appreciative of that. And I would like to say, from my point of view, it was a fascinating talk and I've learned an awful lot. Thanks very much.
Thank you. Thank you. Thank you.